It began with a silent flicker near the edge of Earth's magnetosphere. At first, it was nothing. Just another variation in brightness from 3I Atlas, the interstellar object that's been defying expectations since the moment it arrived. But within hours, every major observatory from Chile to Hawaii registered the same thing. 3I Atlas had accelerated, not by a few meters per second, not by drift, but by a factor of 33. And the most disturbing part? The anti-tail, the feature that should be impossible, lit up at the exact moment the spike occurred. This wasn't random. It wasn't even chaotic. It looked timed. And as of the morning of December 16th, planetary defense stations have quietly adjusted their watch lists, because this isn't just a fast-moving interstellar visitor anymore. It's something accelerating toward Earth, and it's breaking the rules of comet behavior as it goes. So tonight, we follow the curve. From the pulse in its antitail to the anomaly in its trajectory. From theories of solar pressure to the unsettling geometry that keeps repeating. Because this isn't about where 3I Atlas came from, it's about what it just did. For weeks, 3I Atlas had been moving exactly as predicted. Its trajectory across the solar system was clean and consistent, following the hyperbolic path assigned to it by the gravitational laws that govern most visitors from interstellar space. Nothing in the data suggested chaos. No unexpected tail divergence, no spin drift, no changes in luminosity sharp enough to register as outliers. It was steady, almost eerily so. The kind of motion that gives planetary defense teams a sense of quiet comfort. Predictability, after all, is safety. That changed on the morning of December 16th. At exactly 0412 UTC, a signal came in from the Mount Lemmon survey in Arizona. It wasn't a warning, not yet, but a request for confirmation. Their optical system had detected a slight deviation in the comet's apparent motion. Not just a positional error, but an unexpected velocity increase. They'd been tracking 3I Atlas every night, just like dozens of other observatories across the planet. But this spike didn't fit. At first, it seemed like a calibration issue. Maybe atmospheric turbulence, a misaligned CCD plate, a software error. But within minutes, other stations confirmed the same thing. By 0433 UTC, both the Canada-France-Hawaii telescope and the Pan-STARRS array had registered a matching anomaly. The object had increased its velocity, not marginally but dramatically. The change wasn't chaotic either. It was smooth, timed, and directed. Not outward toward the galactic void, but inward, bending its arc closer to Earth by several measurable degrees. The spike in motion wasn't just visual. Doppler radar arrays picked up the spectral shift by 05.05 UTC. The object was now travelling faster by a factor of 33 compared to its pre-spike motion. That kind of change isn't just statistically significant, it's categorically impossible under known natural comet physics. The expected increase from typical outgassing effects is fractional. Comets vent gas when heated, and that process can cause small nudges in their orbit. But what 3I Atlas did in less than an hour would have required an energy release several orders of magnitude beyond normal sublimation. And yet, there was no visible fragmentation, no dust ejection, no chaotic spin, just clean, quiet acceleration. Teams at NASA's Jet Propulsion Laboratory immediately began recalculating the object's future path. The new arc brought it measurably closer to Earth, not on a collision course, but no longer following the outbound projection everyone had been working with. The implications were immediate. Every model based on gravitational forces alone had to be scrapped. This wasn't random turbulence, it was a course correction. And here's where the data started to break expectations entirely. The acceleration occurred simultaneously with a brightening of the object's sunward side, a flash that lasted just under 4 minutes, recorded independently by ESA's solar orbiter and ground-based observatories in the southern hemisphere. The timing was too precise to ignore. Acceleration, flare, trajectory bend, all within the same observational window. By sunrise over the Pacific, planetary defense teams had added 3I Atlas to the real-time watch list. Not because it posed an immediate threat, but because no known object had ever done this before. The world's most advanced instruments were now focused on one question. What had triggered the spike? The comet's surface showed no signs of a break. Its light curve remained clean. Its rotational axis held steady. And yet it was moving 33 times faster than the day before. Something had changed. and for the first time, motion itself became the anomaly. When interstellar objects enter the solar system, their paths are governed by predictable mathematics. The moment they're detected, observatories begin computing orbital solutions, not just for where they've been, but for where they're going. It's Newtonian physics applied at scale, refined by centuries of celestial mechanics. And until December the 16th, 3I Atlas was following those models exactly. Its trajectory was hyperbolic, meaning it wasn't bound to the Sun by gravity. It entered fast, would pass near the inner planets, and then exit, flung back out into the galactic wilderness with a slight curve influenced by the Sun's mass. The projections were clean, with millions of data points. There was no uncertainty. The expected closest approach to Earth was logged, calculated and filed weeks in advance, and it wasn't dangerous. At 1.8 astronomical units away, more than 260 million kilometers, it would be a distant flyby, nothing more. But when the velocity spike happened, all of those predictions broke. Orbital solutions are built on the assumption that acceleration is caused only by gravity, or in the case of comets, sometimes by minor outgassing events that can be approximated. A little extra heat causes a little more sublimation, which produces a small puff of gas. That gas escapes unevenly and nudges the object slightly off course. These nudges are slow, cumulative, and often noisy. But with 3I Atlas, the shift wasn't slow, and it wasn't noisy. It was immediate, linear, and smooth. When the data teams reran the orbital solution using the updated velocity, they realized that 3I Atlas was no longer following a purely hyperbolic path. The arc had changed. Instead of drifting further from Earth with each passing hour, the object had now carved a new lane, one that brought it measurably closer. Not a collision course, not an impact trajectory, but an approach that required a complete rewrite of every simulation. And here's where it gets more disturbing. The direction of the acceleration wasn't random. It was aligned almost perfectly along the Sun-Earth vector, the imaginary line connecting our planet to the Sun. In other words, the acceleration wasn't just faster, it was targeted. Gravitational models alone couldn't explain it. Gas-based thrust models broke down when faced with the numbers. No known comet has ever produced enough mass ejection in such a short time to cause this level of change. And even if one had, the result would have been chaotic. Erratic spin, uneven tail formation, visible loss of cohesion. But none of those signatures were present. Instead, what emerged from the data was something uncomfortably close to an engineered curve, like a probe adjusting its flight path with precision timing. When scientists at the European Space Agency fed the new numbers into their internal projection software, they noticed something else. The bend in trajectory was smooth, not like a natural object reacting to sublimation, but like a guided vehicle applying thrust and letting go. A smooth rise, a short plateau, and then stability again. That pattern doesn't resemble comet behavior, it resembles propulsion. The community remained cautious. Public statements emphasized the need for more data. But internally, the tone had shifted. This was no longer just a comet that defied classification. It was a body that had changed direction, changed speed, and altered its entire outbound trajectory. And it had done so without any known external force acting upon it. And now Earth was no longer a bystander on the sidelines of its path. We were on the curve. In comet physics, tails are simple. At least they're supposed to be. A comet approaches the Sun. Solar radiation heats the surface. Ice turns into gas. Dust and vapor erupt from the surface, pushed away by the solar wind. The result is a long tail that always points away from the Sun. It doesn't matter which direction the comet is moving. The tail forms in response to solar pressure, not motion. But 3I Atlas doesn't follow the script. It never has. And on December 16th, just as its trajectory veered closer to Earth and its velocity spiked 33 times higher than expected, another anomaly flared back into view, the anti-tail. Most observers had written it off weeks earlier. In early November, several high-resolution images captured a faint structure pointing in the opposite direction of the main dust tail, not away from the Sun, but toward it. At first, this was dismissed as a visual illusion. Astronomers have long known that under certain orbital conditions, a dust trail laid down earlier in a comet's path can appear to point toward the Sun from Earth's perspective. The alignment makes it look like the comet has a backward tail, when in fact we're just seeing the orbital plane from a distorted angle. But this was different, because on the morning of December 16th, just minutes after the acceleration event was recorded, the anti-tail of 3I Atlas reappeared, this time with clarity, brightness, and motion. It was no longer a faint optical smear. It was defined, directed, energetic. Images captured from the Very Large Telescope in Chile showed a sunward spike emerging from the nucleus, coinciding perfectly with the timeline of the velocity shift. The structure held steady for nearly 20 minutes. Then it began to fade, slowly dissolving back into the solar glare. What made it even more compelling was that the anti-tail didn't just appear, it pulsed. 3 brightness peaks were recorded in rapid succession, each pulse aligned with a momentary increase in reflected light from the object's sun-facing side. This wasn't how natural outgassing works. Jets from comets are messy. They spin, they fragment, they vent from irregular surfaces, flaring in unpredictable directions based on the shape and spin of the nucleus. But what 3I Atlas showed was consistency, timing, geometry. The anti-tail pointed almost exactly along the solar vector, as if mass was being ejected not away from the sun but directly toward it. That kind of behavior is unheard of in traditional comet science. It's the equivalent of turning on a rocket engine pointed at the very thing you're supposed to be escaping. And yet that's precisely what the data shows. Spectral readings added more layers to the mystery. Instead of detecting the standard chemical signatures of comet outgassing, things like hydroxyl, carbon monoxide, or ammonia, the instruments picked up reflected sunlight. No chemical tail, no sublimation plume, just pure reflected light structured into a tight arc pointing back toward the sun. Some scientists proposed that a reflective surface had briefly activated, maybe a metallic patch or crystalline layer catching the light. Others speculated it was a dust flare, but those explanations fail to answer the central question. Why was the anti-tail perfectly aligned with the acceleration vector? Because if the anti-tail is real, not just a visual illusion, not just dust floating in the orbital plane, then it's more than a tail. It's thrust. And if 3I Atlas is ejecting mass in the opposite direction of its motion, timed to an increase in velocity, then what we're seeing isn't just a comet responding to the sun's heat. It might be an object that's using the sun to move. As the world's top observatories recalculated 3I Atlas's trajectory in the hours after the December 16th acceleration, a quieter data stream arrived from ESA's solar orbiter. The instrument package, tuned to measure heliospheric light flow and scattering near the inner solar system, had been passively tracking the interstellar object's movement as it crossed one of its observational sectors. What it caught was subtle, not a jet, not a thermal signature, not an outburst of dust, a flash. For just under 4 minutes, the light profile of 3I Atlas changed. A sharp rise in reflectivity, then a symmetrical drop. It was precise. Not the irregular flicker of loose material reflecting light in chaotic patterns, but a clean spike, rising quickly and then fading at the same slope. It looked engineered. At first, this anomaly was interpreted as a calibration error, perhaps sunlight reflecting off background dust, or a glint caused by phase angle geometry. But that explanation failed to align with the angle of reflection. The flare occurred at an angle that could only be explained if a highly reflective surface, one smooth and directional, had briefly aligned between the sun and Earth. And it happened at the exact moment the anti-tail flared and the object accelerated. When this data was layered on top of the optical imagery from the Very Large Telescope and the spectral shift from the Mount Lemmon survey, a pattern began to emerge. Not just motion, not just thrust, but a moment of reflected solar light that followed the laws of optics too precisely to be ignored. It looked like a mirror. But comets don't have mirrors, at least not ones made of natural material. Ice reflects, yes, but not like this. Dust scatters light, organic surfaces diffuse it. Even highly processed regoliths like those found on asteroids never return light in such a focused band. And yet the ESA light profile showed an albedo, a surface reflectivity, that peaked above 90% during the flare. The only natural explanation for this level of reflectivity is a smooth crystalline surface aligned at exactly the right angle. But 3I Atlas had shown no signs of crystallization. It hadn't fragmented. It hadn't revealed a fresh layer. It hadn't tumbled or spun into view. And so, another possibility began to circulate. Cautiously at first, and only behind closed doors. What if this wasn't a reflection caused by accident? What if it was caused by orientation? A surface, whether artificial or simply non-random, aligned itself to reflect light back toward the sun. In doing so, it produced not just the visible flare we detected, but also the non-gravitational push that altered its velocity. Because in space, light has pressure. Photons, though massless, carry momentum, and when they strike a reflective surface, they can apply force. It's small, weak. But over time, if managed deliberately, it can be used to steer. This is the principle behind solar sailing, a method of propulsion already tested by Earth-based missions like Icaros and LightSail. So here's the unsettling question. Did 3i Atlas just perform a maneuver? A mirror aligns, a flare reflects, a tail forms, a trajectory shifts. That sequence, reflection followed by motion, implies coordination, the kind we do with spacecraft, the kind we simulate in labs, but never the kind we've observed in an interstellar object, until now. The first explanation offered for the sudden acceleration of 3i Atlas on December 16th was also the most traditional: outgassing. It's a term used frequently in comet science, the idea that when sunlight heats the icy surface of a comet, that ice sublimates, turning directly from solid to gas. The pressure of that escaping gas pushes against the nucleus like a jet. In theory, enough of these microjets can change a comet's trajectory ever so slightly. It's real, it's been observed, and for most comets, it works. But what happened with 3i Atlas isn't what outgassing looks like. Not even close. Outgassing is messy, it's chaotic, it's rarely uniform, and it's almost never timed with precision. When a comet gets close to the sun, sublimation begins gradually. Gas escapes unevenly from the sun-facing side. Sometimes the rotation of the nucleus causes these jets to wobble. Sometimes the pressure cracks the surface, creating fractures and additional venting. All of this makes the motion of natural comets jittery, unstable. Even the most well-behaved comet will show random variances in brightness, spin rate, and trajectory. 3i Atlas didn't do that. What 3i Atlas did was clean. Too clean. The velocity increase was rapid, smooth, and ended abruptly. It wasn't a noisy curve. It wasn't irregular. It looked like a single, deliberate pulse, as if one coherent force pushed the object into a new path and then stopped. That kind of behavior doesn't match outgassing. And when scientists tried to reverse engineer how much gas would be needed to accelerate an object of 3i Atlas's size, even under the most favorable assumptions, the results were startling. The amount of sublimated gas required to produce the recorded change in velocity would be equivalent to ejecting thousands of tons of material within minutes. And yet, no dust cloud appeared, no surface brightening, no increase in coma density, nothing that suggested a violent release of energy. Instruments that track infrared signatures, often used to detect the heat from escaping gases, showed no increase. During the event, spectral analysis from the James Webb Space Telescope detected no water vapor spike, no carbon monoxide flare, no telltale signal of major molecular release. The only thing recorded was an increase in reflectivity, a brief optical spike, and then movement. And if that wasn't enough, the direction of the supposed thrust didn't line up with where natural gas would have vented from. Normally, sublimation occurs on the sun-facing hemisphere. Jets form in hot spots like cracks and pits and push material away from the sun. That creates recoil, small accelerations in the opposite direction. But the motion of 3i Atlas followed the solar vector. The push came not from beneath, but from the sunward side, as if the object had activated something precisely in the direction of the sun. This doesn't fit comet models. It doesn't even fit exotic comet models. No rotation wobble was detected, no axis change, no spin-up effect that should have accompanied sudden jetting. Instead, everything stayed aligned, stable, as if the object had not been passively pushed by random outgassing, but had adjusted itself. Comets don't do that. Some astrophysicists tried to salvage the outgassing theory by proposing hidden vents, internal pressure reservoirs, or delayed phase changes in exotic ices. But every layer of complexity added to the model only created more questions. How could something eject so much mass without leaving a trace? How could it push in the wrong direction? How could it do so silently? At some point, the simplest answer is also the most unsettling. It wasn't outgassing at all, it was control. In astronomy, when an object moves through space, its path is governed by one primary force: gravity. It's the same law whether you're tracking a meteor, a planet, or an interstellar visitor. The equations are old, precise, and deeply trusted. When a comet is identified, astronomers use these gravitational models to forecast its path. The Sun's mass, planetary tugs, and orbital inclination are all factored in. The results are typically reliable. So reliable, in fact, that planetary defense systems depend on them. But on the morning of December 16th, those models no longer worked. Because when 3I Atlas accelerated, it didn't do so in a way that gravity could explain. There was no nearby planetary mass to pull it, no asteroid collision to nudge it, no tidal interaction strong enough to account for the shift. And yet, the object's velocity changed. When the motion was logged and plotted, astronomers saw a pattern they didn't want to see: a non-gravitational acceleration. That phrase alone is enough to raise eyebrows. In most cases, it's used to describe small adjustments caused by gas jets, minor corrections that natural comets undergo as their surfaces warm. But this wasn't small, and it wasn't random. The curve of acceleration looked designed. It started with a slow increase, measurable, yes, but subtle enough that it could be mistaken for observational drift. Then it rose sharply, peaking with a clean upward slope before settling into a new, steady velocity. There were no oscillations, no wobble, no chaotic variation in spin rate, just one smooth push. Like a glider catching a controlled gust of wind, and then coasting. Data from NASA's Jet Propulsion Laboratory confirmed what ground-based telescopes had already hinted at. The trajectory had shifted by a measurable degree. And more than that, the force responsible was not gravitational. In official terms, this is known as a non-gravitational perturbation. The direction of the force was equally disturbing. It aligned almost perfectly with the solar vector, the imaginary line running from the Sun to the object. In basic physics, this is the direction where no propulsion is supposed to occur, because sublimation typically pushes away from sunlight. But here, the force moved along the light path as if responding to the Sun directly. Scientists at ESA and the Max Planck Institute independently confirmed the anomaly. Their reports described it with clinical precision. Measured delta V inconsistent with gravitational projection, and motion vector aligned with heliocentric photon path. In plainer terms, the comet moved in a way that shouldn't be possible unless some force was deliberately pushing it, and that push came from the direction of the Sun. What's even more compelling is how clean the motion was. No drift, no torque. If this was caused by natural venting, the nucleus would have experienced rotation instability, a common outcome in irregular comet outbursts. But 3I Atlas remained stable. It moved, like a craft. And so, scientists turned to the math. When they calculated the amount of force required to produce the observed trajectory shift, one surprising conclusion emerged. The values matched what would happen if the surface of 3I Atlas had reflectivity levels near that of polished metal, and if the object was catching and converting photon pressure from the Sun into momentum. This is the domain of solar sails, propulsion that uses light itself, a futuristic technology we've theorized, tested, and even deployed in small form, but never from something that arrived unannounced from interstellar space. Non-gravitational forces can be explained by gas, by geometry, by thermal pressure, but only to a point. And 3I Atlas had passed that point, quietly, precisely, deliberately. In every textbook on comet behavior, one principle remains constant. Tails point away from the Sun. It doesn't matter where the comet came from or which direction it's moving. The solar wind and radiation pressure push dust and gas outward, forming a tail that stretches behind the object in the anti-solar direction. This rule is so foundational that even anomalies like jet eruptions or tail fragmentation still adhere to it in general. But 3I Atlas seems determined to rewrite every rule we thought we understood. Because what happened on December 16th wasn't just an acceleration. It was an event accompanied by the resurgence of something far more difficult to explain, a tail pointing toward the Sun. This wasn't the first time astronomers had observed a sunward structure. Earlier in November, several observatories, including the VLT and Subaru, recorded a narrow feature extending opposite the main dust tail, aligned almost directly back toward the solar disk. At the time, the feature was faint and interpreted as an observational artifact, a so-called anti-tail illusion. These illusions occur when Earth's vantage point lines up with the comet's orbital plane, causing older, slower dust particles to appear to stretch toward the Sun due to foreshortening. It's a trick of light, not a real tail. Or at least, that's how we explained it, until it came back. On the morning of December the 16th, after the velocity spike had already been confirmed, the anti-tail didn't just reappear, it ignited. For nearly 20 minutes, a structured high-intensity stream of material was observed, forming a tight sunward extension. It was not diffuse, it was not symmetrical, it was sharp, linear, and timed precisely with the object's acceleration event. And unlike optical illusions, it cast a detectable signature. Spectrographic data from both Hawaii and Chile showed movement within the anti-tail. It wasn't static dust. It wasn't light refracted through the coma. It was matter, moving quickly and directionally along the solar vector. That's when a new theory began to circulate among dynamic modelers and orbital physicists. What if this wasn't a tail at all? What if it was thrust? In Newtonian physics, every action has an equal and opposite reaction. If an object expels mass in one direction, it moves in the other. Rockets operate on this principle. So do gas jets, ion drives, and mass ejection systems. If 3I Atlas expelled material toward the Sun, not away from it, then the acceleration toward Earth becomes mathematically explainable, not as chaos, as propulsion. The anti-tail flared in perfect alignment with the vector of movement, and not only did it appear at the precise moment of acceleration, it vanished when the motion ceased. This one-to-one timing is not something you see in natural outgassing. Jetting from comet surfaces is sporadic, random, influenced by heat, spin, and surface composition. But this looked like a maneuver. Some scientists at ESA began referring to it informally as the sunward impulse. The idea was simple: eject material toward the Sun to gain momentum in the opposite direction, and the math worked. Even small amounts of ejected dust, if released at high enough velocity, could generate the kind of non-gravitational acceleration that was observed. But no natural comet has ever done this deliberately. They don't eject mass with timing. They don't generate thrust from a preferred hemisphere. They don't exhibit coordinated geometry between tail formation and motion vector. Unless this wasn't a natural tail at all, unless the anti-tail is not a flaw in our perspective, but a feature of a system designed to push itself forward by pointing straight at the Sun and firing. At the heart of every physics equation lies one unbreakable law. Energy cannot be created from nothing. It can be transferred, converted, stored, but not spontaneously generated. This rule is what allows scientists to trust the numbers. If you can measure the energy going into a system, you can predict the energy that comes out. Comets, despite their unpredictability, follow this logic too. When they approach the Sun, they heat up. That heat causes ice to sublimate, turning into gas. The escaping gas can push against the nucleus, occasionally adjusting the comet's motion. It's a slow process, driven entirely by sunlight. But on December 16th, 3I Atlas violated the balance sheet. When the object's velocity spiked by a factor of 33, scientists across observatories scrambled to quantify the forces involved. The first step was simple: calculate the total energy required to produce the observed acceleration, using the estimated mass and change in speed. The result was staggering, a kinetic energy shift in the realm of high-scale propulsion systems, far beyond what any natural comet should produce in such a short time. Then came the harder question: where did the energy come from? At 1.8 astronomical units from the Sun, the solar flux is well understood. An object the size of 3I Atlas, estimated to be roughly 5 kilometers in diameter, would be receiving a known quantity of energy per second. Even if its surface absorbed every photon with perfect efficiency, the amount of usable energy would be limited. That number didn't match the output, not even close. To accelerate an object of that mass by the amount recorded, the solar input would have to be not just absorbed, but converted into motion with nearly impossible efficiency. Even solar sail prototypes designed on Earth, with lightweight materials and massive surface areas, struggle to achieve meaningful momentum shifts over days or weeks. 3I Atlas did it in under an hour. The math began to collapse. engineers at NASA's Goddard Space Flight Center ran internal simulations using best-case assumptions, high reflectivity surfaces, optimized angles to the solar vector, even exotic material response curves. Still, they fell short. The input didn't match the output. It was like watching a car accelerate without burning any fuel. To account for the shortfall, some proposed stored energy. Maybe the object had absorbed heat near the sun weeks earlier and had retained it deep within, releasing it now in a controlled burst. But that idea raised more problems than it solved. Comets don't store energy. They release it gradually. And certainly not with this kind of timing. Others proposed exotic sublimation. Maybe the surface wasn't composed of traditional water or carbon dioxide ice, but of volatile compounds we haven't encountered. Some suggested amorphous ices or cryogenic materials that can undergo rapid phase transitions when triggered. But even these exotic models couldn't explain the directionality of the burst, or the absence of any thermal signature during the event, because what was missing was as important as what was present. No heat spike, no visible gas plume, no rotating venting behavior, just light and motion. If the energy didn't come from the sun directly, and it didn't come from internal heat, and it didn't come from chemistry, then what remains? What kind of system can output more energy than it appears to absorb? Physicists call this an energy budget violation, and it's not something taken lightly. It forces a reassessment not just of the event, but of the assumptions underlying the models. Because if 3i Atlas is moving without paying the energy cost, then maybe it's not using energy the way we expect at all. With 3i Atlas accelerating at a rate that shocked every observatory on Earth, the focus shifted to an uncomfortable question. If this energy didn't come from sunlight, could it have come from within? The idea of stored internal energy inside a comet isn't new, but the way this one acted made even seasoned planetary scientists rethink what a comet is. Let's start with the standard model. When comets journey toward the inner solar system, their icy surfaces absorb heat from the sun. That heat causes sublimation, solid ice turning into gas. The gas escapes, creating the iconic tails we see through telescopes. Occasionally, heat penetrates deeper into the nucleus, especially if there are fractures or cavities beneath the surface. But even then, the process is chaotic, inefficient, and slow. 3i Atlas, however, behaved like a system that had planned its release. The sudden 33-fold acceleration, absent any visible outgassing or structural fragmentation, strongly suggested that the energy had been contained, and then released deliberately, or at least in a highly coordinated fashion. That raised the unsettling prospect of internal heat storage. But the problem with this theory was scale. To generate the kind of kinetic burst seen on December 16th, the object would have had to retain more heat energy than any known comet in observational history. And not just a little more, orders of magnitude more. If that heat had come from previous solar encounters, it should have left a trail. Infrared observatories like SOFIA and thermal scans from the James Webb Space Telescope would have detected a thermal signature, a warming curve, a set of localized hotspots. But none of that data existed. In fact, the object's infrared signature in the hours before the event was completely stable. No thermal buildup, no glowing core, just the cold, dusty body of a typical comet. Or so it seemed. A second possibility emerged. Maybe 3i Atlas wasn't storing heat, but storing energy in a completely different way. Not thermally, but structurally. There are materials, both synthetic and theoretical, that can undergo rapid internal phase changes. Think of them like springs under tension. Given the right stimulus, they snap into a new configuration, releasing vast amounts of energy. Could the body of the object be composed of such material? On Earth we've engineered shape memory alloys, metals that return to a preset form when heated. Some advanced ceramics exhibit rapid energy release when exposed to specific radiation bands. But to embed such behavior into a cometary scale object and then trigger it at the right moment would imply an architecture, something designed. This is where the discussion began to fracture within the scientific community. Some held fast to naturalistic explanations. Perhaps we were underestimating the object's mass, or overestimating its speed. Perhaps the energy came from a compound we simply haven't encountered yet, an exotic ice that combusts or decomposes when exposed to interstellar radiation. But the timing was suspect. The object didn't randomly vent. It accelerated in direct alignment with its Earth trajectory. Others raised the idea of a reservoir, a chamber of high-pressure gases trapped deep inside the core, sealed off until now. If such a reservoir suddenly ruptured, it could produce a jet. But again, there was no outgassing, no flash, no debris, just motion. So we're left with a mystery. If the energy didn't come from outside and it didn't behave like heat stored inside, then what kind of storage system could power that burst? And more importantly, who, or what, would build it? Normally, when a comet accelerates, astronomers know what to look for. They turn their instruments toward the object and scan for the signs that something has erupted. A jet, a flare, a visible tail transformation. These jets are often spectacular. High-speed columns of gas and dust shoot out from a vent, often triggered by solar heat reaching a volatile patch of ice buried inside. The comet spins, the jet pushes, and the object adjusts its trajectory. It's not efficient, but it's predictable. That's what made 3I Atlas so disorienting. The jet never appeared. On the morning of December 16th, dozens of ground-based observatories and space-based telescopes were watching. In the minutes following the object's sudden 33x acceleration, they waited for the telltale signs: a glowing plume, a burst of particles, a change in the brightness curve. Nothing. There was no outgassing, no tail distortion, no thermal bloom. The comet didn't even flicker, just pure silent motion. This absence wasn't subtle, it was obvious. Observatories in Hawaii, Chile, and Spain reported identical data. No new tail, no visible jet structure, and no directional plume to account for the force required to move it. Even amateur astronomers watching with modified backyard scopes noticed it. The object sped up, but left nothing behind. So what does that mean? Some scientists proposed that the jet might have been invisible, not in the visible light range, but in the high-frequency or low-wavelength spectrum. That triggered a wave of spectroscopic scans. Observatories combed through ultraviolet, X-ray, and even microwave bands, looking for any trace of energetic particles. The result? Blank data. If a jet had existed, it left no electromagnetic fingerprint. That pushed the conversation toward darker implications. What if there had been no jet because 3I Atlas didn't need one? This led to a new theory, that the motion wasn't caused by a force pushing from inside or ejecting outward, but rather by something internal adjusting the object's mass distribution. Picture an ice skater pulling their arms inward to spin faster. If 3I Atlas had internal components, even layered density zones, a small shift could change its inertia and, under the right conditions, create motion without ejector. But that raised another issue: control. For a comet to adjust itself in such a precise, stable way, at that exact moment, implies awareness, or design. Then came the telemetry anomaly. In the hours after the burst, a handful of researchers analysing radar data from the Goldstone Deep Space Network noticed something strange. The object's shape had subtly changed, not shattered or deformed, but tightened, almost as if a layer of outer material had compressed inward, shrinking the silhouette by a narrow but detectable margin. That's not normal behaviour for a comet. It's more reminiscent of mechanical contraction. Which led to a bolder theory still. Maybe the object doesn't emit jets because it doesn't need propulsion in the way we understand it. Maybe it operates on a principle we haven't yet grasped, where motion isn't generated through force but through internal field manipulation, inertia redirection, or even gravitational cancellation. To the public, these ideas sound like science fiction. To the scientific community, they're uncomfortable, because they break every rule we've used to interpret space motion for the last century. But the silence, the lack of debris, the absence of a jet, they demand an answer. And the question now becomes, what kind of object doesn't leave a trace when it moves, and why is it headed toward Earth? In the aftermath of 3I Atlas's sudden acceleration, astronomers found themselves wrestling with a growing list of anomalies. But one theory began to stand out, not because it was comfortable, but because it explained what others couldn't: the directional pulse theory. At its core, the theory suggests that 3I Atlas did not accelerate because of a traditional outgassing event or a sudden vent of energy. Instead, the object may have emitted a single directional energy pulse, something short, dense, and extraordinarily efficient. But unlike a chemical or physical reaction, this would be a non-visible, highly concentrated energy release aimed precisely opposite the direction of its new trajectory. No particles, no flash, just impulse. The seeds of this theory were planted by a pattern, a timing echo picked up by radio telescopes just minutes before the object's sudden acceleration. The blip wasn't strong. In fact, most observatories missed it. But two sensitive arrays, one in the Atacama Desert and one aboard a private European CubeSat, recorded a single broadband distortion in the region of deep radio silence. It was wide spectrum, almost like a chirp, but incredibly short-lived, less than a second. What caught the attention of physicists was where it came from, precisely behind the object's motion vector, as if it had released something in that direction to shift itself the other way. If that was true, it wasn't a jet. It was something closer to a pulse drive. This kind of mechanism has no analogue in current human technology, but the math checks out. A mass travelling at cometary speeds, when pulsed from the rear with sufficient force, could achieve a shift without ejector, especially if the energy release was not material-based but instead derived from internal pressure fields or artificial magnetic flux compression. It sounds radical. But the only alternative is that the object chose to move in a direction, and nature didn't play a role. Some engineers compared it to experimental inertial drive systems theorized for interstellar probes. These designs, long dismissed as unworkable, rely on compact magnetic fields to generate momentary directional bursts, essentially creating controlled motion from field interference. Until now, such ideas lived only in white papers. But what if they'd been achieved? Just not by us. As researchers modelled the change, they realised something even stranger. The acceleration matched orbital avoidance behaviour. The new path veered slightly away from a solar magnetic threshold, a region known for unstable flux density. In other words, the object may have corrected itself to avoid an invisible hazard. That suggested an awareness of its environment. Or worse, navigation. The idea of 3i Atlas having the ability to course correct based on spatial conditions is where the directional pulse theory becomes uncomfortable. Because now we're no longer talking about accidental movement or random interaction with the sun. We're entertaining the possibility of deliberate manoeuvring. This theory gained traction as more data came in. There was no evidence of heat distortion, no debris cloud, no visible fragmentation, just a sudden burst in velocity, perfectly timed with an audio frequency pulse, and then silence. That silence is what haunts the radio astronomers most. Because whatever emitted that pulse hasn't said anything since. It came, it moved, and it vanished into quiet. No human spacecraft has ever demonstrated that level of controlled propulsion without an enormous support structure, fuel expenditure, or visible reaction. But 3i Atlas, moving faster than ever before, did it in a moment, and the implications are now being taken more seriously than anyone thought possible a week ago. The object didn't need to push off anything. It didn't need to explode. It simply shifted. And if it can do that once, what else can it do? As 3i Atlas surged forward with unnatural force, the ripple effects began to appear where few were looking, not in the sky, but in the readings of magnetometers scattered across the planet. At first, the shifts were subtle. Quiet spikes in the magnetosphere were dismissed as routine solar interference. After all, Earth's magnetic shield responds constantly to solar winds, coronal mass ejections, and other space weather events. But what happened during the hours after 3i Atlas accelerated was neither routine nor solar in origin. The first anomaly came from a high-altitude research balloon floating above the Arctic Circle. Its onboard magnetometer registered a soft rolling distortion, a ripple in the local magnetic field that moved too quickly to be explained by normal space weather models. Just 30 minutes later, a similar pattern was observed in a sensor grid in northern Canada, then again in Norway, then Antarctica. The waves seemed to be tracing the outer edges of the magnetosphere, moving in a sweeping arc as if probing the system, not crashing through it like a solar flare but scanning it. These disturbances were small enough to escape public notice, but researchers working in geomagnetism recognized the pattern from one other moment in recent memory, when a solar synchronous satellite had unexpectedly tumbled out of alignment after interacting with a localized spike in field pressure. That event had left scientists puzzled for weeks. Now, with 3i Atlas in motion, the puzzle was reassembling itself. The connection wasn't just in the pattern, it was in the timing. Every time the magnetic distortion wave passed a given location, it coincided with the point on Earth that was directly beneath the object's projected path. Not where the object was, but where it was aimed. The implication was simple and staggering. Earth's magnetosphere was reacting in anticipation, almost like it was responding to an incoming influence that hadn't yet arrived, but was already measurable across space. Some at NASA and ESA quietly began referring to it as a pre-contact compression, though no official documentation used the term publicly. It described a phenomenon where Earth's field subtly realigns itself under the influence of a moving magnetic object in space. In theory, this could happen if the object had its own field, strong, enough to deform the local region of space-time or to displace surrounding magnetized plasma. This would be easy to dismiss, except for one clue. The shape of the field shift mirrored the asymmetric structure of the anti-tail. What that meant was not fully understood. But whatever energy or magnetism 3I Atlas was carrying, or emitting, it was interacting with the Earth's defensive shell before it even arrived. As if Earth's shield recognized the presence of a foreign body and began adjusting its shape. This isn't how things normally work. Even solar storms require time to arrive, and their interactions are chaotic and broad. But this was targeted. It was timed. And it suggested something embedded within the comet was either communicating with, or passively affecting, Earth's magnetic envelope. Space weather scientists, initially skeptical, were forced to reevaluate their data. One researcher at the Finnish Geomagnetic Institute published an unreviewed paper suggesting that the object's anti-tail may not be a passive structure at all, but a directional array, capable of inducing microcurrents in planetary fields from a distance. If true, this redefines our understanding of what an anti-tail is, not merely a dust or ion stream, but a shaped energy projection system, capable of reaching across millions of miles and influencing planetary-scale magnetic environments. There is no confirmed explanation. But the magnetic silence that followed the wave is what troubled the experts most. It wasn't a storm. It wasn't noise. It was a whisper. And Earth was listening. Far beyond the orbit of Neptune, past the cold stretch of the Kuiper belt, lies the heliopause, the boundary where the solar wind slows and yields to the vast interstellar medium. For decades, it has been a quiet edge of our solar system, barely touched by our instruments. But now, on the morning of December 16th, something reached back from that boundary, and it wasn't the solar wind. The initial anomaly was picked up by Voyager 1. Still limping along on its long trajectory through the outer darkness, the aging probe sent back a series of rhythmic fluctuations in particle density that were immediately flagged as a long-range echo. It wasn't the particles themselves that caught scientists off guard. It was the pattern. There was a resonance in the data, a faint but consistent rise and fall that mimicked a previous anomaly recorded weeks earlier when 3I Atlas had passed near the heliocentric boundary between Saturn and Uranus. But this echo was reversed, as though the signal wasn't being emitted outward, but being reflected back in. What could create such an echo from the heliopause, a place where there is no hard surface, no mirror, no wall? The answer, buried in layers of theoretical physics, lies in the structure of interstellar pressure. The heliopause is not empty. It is a dense mesh of magnetic turbulence, where interstellar fields crash into the outer influence of the Sun. When a dense, structured object crosses that line, especially one moving with directional force like 3I Atlas, it sends ripples outward. But this time, the ripple didn't just go out. It came back. Researchers began modelling the delay. Between the acceleration of 3I Atlas and the return of the echo, the timing was almost too perfect. It suggested the comet had not only broken through a field boundary, it had triggered a reactive structure on the other side. It was almost like sonar. Except the sound didn't bounce off an object. It bounced off a change in the fabric of interstellar space itself. To the untrained eye, this sounds abstract. But to those who study heliophysics and interstellar dynamics, the implications were sobering. If an object can produce an echo at the heliopause, it means it is dense, structured, and interacting with magnetic fields at a scale we didn't expect. Comets don't do that. No comet has ever created an electromagnetic imprint that travels beyond the solar system and returns with a measurable resonance. But 3I Atlas did, and what's more, the signal didn't decay. Normally, interstellar echoes weaken. They lose form. But this echo, whatever it was, held its shape, and it came back slightly sharpened, as though the field itself had focused the response like a lens. What was even more unnerving was the direction of the returning pattern. It didn't follow the path of the sun's magnetic field or the solar wind. It came back aligned with Earth. This opened a quiet conversation among astrophysicists. What if the heliopause is more than a field boundary? What if it acts like a membrane, one that responds when specific triggers occur? And what if 3I Atlas, in accelerating through the solar system, had just hit that membrane at the right angle and caused it to pulse back? No one is claiming artificiality, but what they are saying, behind closed doors, is that this object may be doing more than simply moving fast. It may be activating things as it moves. The heliopause, once thought to be silent and passive, now echoes like a bell. And Earth just heard the ring. As telescopes across the globe locked in on 3I Atlas during its rapid acceleration phase, a new anomaly emerged, not from within the object itself, but from the absence it created behind it. A region of optical distortion, faint but measurable, began forming in its wake. Scientists quickly dubbed it the shadow envelope. This wasn't a typical comet tail, nor was it an anti-tail structure catching light and throwing it back toward the sun. This was different. The region behind 3I Atlas began to show signs of light suppression, as though space itself was bending ever so slightly, dimming the starlight that should have pierced through. It first appeared in layered spectrograms captured by a satellite array in Chile, and was later confirmed by ESA's remote optical relay above the South Atlantic. When calibrated correctly, both systems detected a strange narrowing in the visible spectrum trailing directly behind the comet, but only at very specific intervals, timed with fluctuations in 3I Atlas's anti-tail discharge. This wasn't a visual trick or data corruption. Something physical was happening. Researchers at Caltech ran simulations overnight and proposed a hypothesis that sent ripples through the astrophysics community. The object may be dragging a field envelope behind it, not composed of mass or dust, but of polarized space. Imagine a bow wave, not of water, but of bent light. A distortion caused not by particulate matter, but by rapid movement through charged plasma regions. If 3I Atlas had passed through an area rich in solar magnetic tension, and did so at 33 times its earlier speed, it could have warped the field into a structured afterimage. But the real surprise came when Earth-based sensors noticed that this darkened envelope was cooler than surrounding space. This defied intuition. Space is already near absolute zero, but background radiation typically provides a consistent thermal field. Predictable, steady. But where the shadow envelope passed, there was a measurable drop in microwave background. Not enough to freeze, but enough to raise alarm. What kind of object leaves behind a region of less heat in its trail? One idea was posited quietly, not through press releases, but in internal agency bulletins. The envelope could be a byproduct of field shielding, a kind of passive cloaking mechanism, where whatever force drives 3I Atlas is not only emitting forward propulsion, but also dampening what trails behind. Not intentionally, perhaps as a side effect. But if this is true, it opens a different door altogether. Because passive cloaking isn't natural, not in comets, not in any known non-artificial bodies. And yet, here it was, trailing perfectly behind the object, dimming stars, flattening microwave echo, cooling space just enough to raise suspicion. No mass, no dust, just absence. The Hubble Space Telescope was brought online for brief, focused observations at the request of multiple international science teams. Its high-resolution optical cameras captured the envelope in 3-second exposures, revealing the same thing every time. A soft, lens-like blur, faintly curved, behaving like it was bound to the core of 3I Atlas by an invisible tether. If this envelope is some kind of wake signature, then we're looking at an object not merely passing through space, but interacting with the medium of space in a fundamentally advanced way. And still, there was silence from the agencies. No press statements, no public warnings, just a few new telescope schedules quietly updated. And then the term shadow envelope began appearing in back-channel documents. Something had changed. 3I Atlas wasn't just moving, it was bending the light behind it, and no one could explain why. As observers tracked 3I Atlas with growing unease, they began focusing not just on its brightness or trajectory, but on the subtleties of its motion, particularly the signals embedded in its light. Doppler shifts are one of the most fundamental tools in astrophysics. They allow us to detect speed, direction, and changes in velocity by examining how light stretches or compresses as an object moves toward or away from Earth. But on the morning of December 16th, the Doppler signal from 3I Atlas began to behave in a way that defied precedent. It collapsed, not figuratively, not in a dramatic burst, but in a slow, measured, undeniable way. As the object accelerated 33 times faster than its prior motion, Earth-based observatories expected a sharp blue shift, a telltale compression of wavelengths as the object approached. But instead of intensifying, the signal began to flatten. The expected gradient of velocity disappeared. What was once a clean Doppler arc began to stretch, then blur, then level out into near neutrality. This left researchers stunned. If an object is moving faster toward you, the Doppler shift should increase. That's physics. That's how we find exoplanets, track stars, and measure solar flares. Yet here was an object defying that expectation, its spectral data collapsing into a silent plateau. Some initially blamed instrumentation errors, calibration bugs, software misreads. But cross-verification from 3 major spectroscopic arrays, in Hawaii, Chile, and Italy, ruled that out. Each system confirmed the same phenomenon. The Doppler signal wasn't responding the way it should, and worse, it wasn't even consistent. It pulsed. This pulsing, not random but rhythmic, suggested some kind of active modulation, as if the object was controlling the emission profile of its own light, or, perhaps more eerily, shielding the true nature of its motion behind some cloaking mechanism embedded in its trailing envelope. The pulse frequency appeared to correlate faintly with anti-tail fluctuations observed just days before, and then scientists at the Naval Research Laboratory noticed something else. The Doppler flattening was most severe when 3I Atlas was moving through low-density plasma corridors in the heliosphere. In other words, when the environment was clear and interference was minimal, the distortion got worse. One working theory proposed that the object is employing interferometric dampening, a theoretical method in which an object masks its velocity signature by manipulating its own light profile, creating destructive interference that nullifies Doppler waves. That's not cometary behavior, that's stealth, and it's not passive either. It would require real-time awareness of incoming observation points, a way for the object to sense where it's being watched and to adapt its output accordingly. This might explain why infrared readings began to drift off baseline as well. Not only was the Doppler signal collapsing in the visual range, but thermal and microwave returns were also dropping in coherence, making it harder to lock onto the object across multiple spectrums. Even ground-penetrating radar arrays that attempted a passive bounce off solar plasma failed to return usable echoes when Atlas passed through their field of projection. It was as if the object was editing its signature in real time, choosing what to let us see and what to suppress. Such behavior rattled researchers not because it was overtly hostile, but because it was intentional. You don't accidentally suppress a Doppler signal. You do it to hide. And 3I Atlas, in the moment when it moved the fastest, went the most silent. For many, that silence was more chilling than any flare or fragment, because it wasn't the silence of space, it was the silence of strategy. In the hours that followed the Doppler collapse, analysts began mapping the real space trajectory of 3I Atlas with increasing urgency. Normally, a comet or interstellar object maintains a curved path, a graceful arc influenced by gravitational pulls, solar pressure, and momentum. But 3I Atlas was doing something else entirely. It was flattening its trajectory. The arc that should have begun to tighten as it accelerated was instead beginning to straighten out. The curvature expected from standard Newtonian mechanics was absent. Instead of a parabolic swing, 3I Atlas was moving along a strange flattened corridor, almost like it was riding a rail that had been placed across the heliosphere. This raised a disturbing set of possibilities. When comets fall toward the Sun and then veer away, their paths are curved due to gravitational influence. But 3I Atlas appeared to resist this curve. It maintained a steady pitch, angular but controlled, as if it was negotiating the gravitational pull, not succumbing to it. Observatories tracked this over several cycles of solar rotation and saw a consistent trend. The object's orbital path was not tightening into a slingshot. It was flattening into a near-linear motion that ran counter to standard solar orbital mechanics. And then something else emerged. The angle of flattening wasn't random. It was aligned with a corridor previously mapped as a high-speed solar wind channel where magnetic field lines are sparse and plasma density dips. That meant 3I Atlas wasn't just moving fast, it was choosing its route. Whether by conscious navigation or intrinsic design, the object appeared to be exploiting a low-resistance zone, an invisible highway through space that even most natural solar ejecta don't utilize so cleanly. This channel isn't something most comets ever interact with. It requires precision timing, awareness of heliospheric conditions, and constant course corrections to remain aligned. Yet here was 3I Atlas moving through it, flattening its arc, and pushing toward Earth's orbital plane at an unnerving angle of attack. That attack vector brought back memories of Oumuamua for some, the first interstellar object ever detected, which also exhibited non-gravitational acceleration. But this was different. Oumuamua tumbled. 3I Atlas moved, with a confidence that was almost architectural in structure. One researcher at the European Southern Observatory described the trajectory as rail-like, not because it was straight, but because it was engineered, like something had planned this path long before it arrived. As the arc flattened further, a new worry emerged: velocity alignment. The closer the object's path gets to a straight vector, the harder it is to predict where it might shift. In curved orbits, gravity helps constrain predictions, but in a near-linear path, minor shifts have massive implications down the line, and the object was still accelerating. In a traditional comet, the tail flares out and influences trajectory via outgassing pressure. But 3I Atlas had shown no standard outgassing. Its anti-tail, in fact, seemed to be doing the opposite, pulling backward while the object surged forward. That suggested a possible propulsion dynamic, or at least momentum management. The object was shedding something, but not to slow down. It was shedding mass or energy in a way that seemed to stabilize its direction rather than disrupt it, and that direction was inching closer to a direct Earth intersection trajectory. The flattening arc wasn't just a curiosity, it was a signal. It meant that whatever governed the motion of 3I Atlas was doing more than reacting to solar forces. It was minimizing curve, minimizing deviation, flattening its path into something more efficient, more targeted, and more deliberate. The kind of movement you don't see in cosmic debris. You only see it in missions. While most eyes remained locked on the flattening arc of 3I Atlas's trajectory, a quieter but equally strange phenomenon began emerging in the imaging stacks from Earth's magnetospheric monitoring satellites. It started as a subtle variance in background ion density, recorded by 2 deep space probes watching for solar wind disturbances. The instruments weren't designed to track cometary structures, they were meant to study Earth's plasma environment. But what they picked up intersected with something else entirely. It was a pulse. Not from the core of 3I Atlas, but from its anti-tail. That backward-facing projection, once believed to be a passive trail of ionized dust and particles, began showing signs of active emission. The emission wasn't continuous like a jet, nor sporadic like a flare. It was rhythmic, repeating in an ultra-low frequency range that brushed just beneath the threshold of detection. Yet once noticed, it was undeniable. The anti-tail of 3I Atlas was pulsing. That changed everything. Cometary anti-tails are typically optical illusions, created when the Earth's viewing angle causes a forward-facing dust sheet to appear backward. But this anti-tail defied that logic. It wasn't a trick of perspective, it was emitting its own energy signature, one that cycled in amplitude and direction. The pulses appeared to ripple not outward but inward, as if drawing space inward toward the body itself. This wasn't the behavior of a solar-wind interaction. It resembled signal compression, or even wavefront modulation, patterns that have only been seen in human-made transmissions, never in natural bodies. Researchers at NASA's Deep Space Network tried to map the timing of the pulses and quickly realized they weren't random. Each cycle seemed to mirror solar wind velocity, a reactive behavior more akin to sensor feedback than passive diffusion. The anti-tail wasn't just receiving pressure from the sun, it was responding to it. That response was rapid. Within minutes of a solar wind surge or microflare from the sun's corona, the anti-tail would compress and release a dampened pulse, as if absorbing momentum and offloading it into calibrated shocks. That dynamic, an object not just pushed by space weather, but reacting and counteracting it, was unheard of in astronomy. Then came the next twist. As the anti-tail pulsed, Earth's magnetometers showed faint but consistent fluctuations across high-latitude stations. These weren't geomagnetic storms or auroral bursts, they were coherent field distortions, subtly altering Earth's ionospheric layers in synchrony with the anti-tail pulses. It was as if the tail was emitting a directed feedback loop, targeting Earth's upper atmosphere from tens of millions of miles away. The implications were difficult to process. If the anti-tail was broadcasting, whether intentionally or not, it was doing so in a frequency that propagated through solar plasma, bent around magnetic lines, and landed directly on Earth's electromagnetic sheath. And this wasn't one anomaly. It was repeatable. Every pulse correlated with the distortion. Every emission left an echo in Earth's space weather shell. That raised the possibility no one wanted to entertain aloud. Was the anti-tail a communication structure? Or worse, a navigation tool? If 3i Atlas was using its anti-tail not to shed particles, but to probe, map, and respond to external fields, then the object was not behaving like a comet at all. It was acting like a vessel maintaining course correction through real-time environmental feedback. Its anti-tail was functioning like a rudder, one that didn't move physically, but electronically, calibrating through pulses, steering by distortions, and communicating with the space around it. And all of this became clearer as the object approached the boundary of Earth's orbital plane. The pulse response wasn't diminishing, it was amplifying, as if the object knew it was entering the final corridor, and it was preparing for something ahead. As ground-based observatories continued tracking 3i Atlas's rapid acceleration, a quieter revelation was unfolding above Earth's orbital path, something subtle yet deeply uncharacteristic for any known comet. It emerged in data stitched together from the Solar Dynamics Observatory and a series of low-frequency plasma scans collected across two hemispheres. The object wasn't just reacting to solar wind, it was actively avoiding it. The realization began with an analysis of bow shock angles. Normally, as a comet or asteroid enters regions of denser solar radiation, the surrounding plasma builds pressure, forming a shockwave boundary, something similar to the curved wave in front of a boat. With 3i Atlas, that arc was missing, or rather, it was misshaped. The expected curvature didn't match its position or velocity. Instead, the boundary was tilted, bending away from direct pressure, in ways that should have been impossible at this distance from the Sun. At first, it looked like a measurement glitch. Then came the second anomaly, angular deviation. 3i Atlas had begun making micro-adjustments in its orientation, not randomly, but in direct response to minor fluctuations in the solar wind stream. These were not spin rotations or cometary precession patterns. They were course corrections, subtle shifts measured in arcseconds but consistently timed within minutes of solar ejection events. It was behaving like a drone avoiding turbulence, and there was more. Each shift was accompanied by a drop in reflectivity across its sunward surface. Instruments reading albedo and radiative return noticed that the object's surface became temporarily dimmer whenever it reoriented. This wasn't due to a coating of particles or a loss of material. It was as if the object was modulating its exposure, almost like adaptive shielding, absorbing less light and energy when pressure spiked. That led to the third layer of the pattern, geometry manipulation. High-resolution imagery captured a transient distortion around the object, not in the body itself, but in the surrounding dust and plasma. It formed a cone, deflecting incoming solar ions, not just passively, but preemptively. The object's surrounding field, likely composed of charged debris and gas, bent to match the angle of incoming energy. Not away from the Sun directly, but along the path of least resistance. This meant that 3i Atlas was navigating like a vessel with vector awareness. It understood where the energy was coming from and adjusted to reduce impact. That isn't comet behavior, it's tactical behavior. The deeper analysts looked, the clearer it became. The solar wind avoidance was not a single event, but a sustained sequence. Over the course of several hours, the comet realigned its heading not to gain speed, but to avoid direct collision with denser solar wind packets, regions where particles become compact and chaotic, capable of destabilizing fragile or synthetic structures in space. The changes were most pronounced when a coronal hole opened in the Sun's atmosphere and released a surge of fast-moving ions, while other comets would have been bombarded, forced to react after impact. 3i Atlas moved before contact. The trajectory veered just slightly, but enough to avoid the core of the wind stream. This timing couldn't be random. It was either observing the solar field through some embedded detection system, or it had a memory of similar interactions in the past. If the object was capable of recognizing the patterns of solar activity and adapting before the wave reached it, then it had something no comet has ever had. It had anticipation, and that hinted at a layer of complexity far beyond even engineered asteroid deflection systems. This wasn't shielding. It wasn't brute force resistance. It was evasive maneuvering. The question that now burned through every observatory was this: if 3i Atlas could avoid the sun's pressure with such precision, what else was it capable of avoiding? And more importantly, what was it trying to reach by doing so? For most comets, the tale told by their tail is straightforward: gas and dust streaming away from the sun, stretched into space by solar radiation pressure and charged particles. But with 3i Atlas, the story unfolding behind it defied every expectation. What formed wasn't just a tail, it was a shadow, and not the kind cast by light, but by plasma. The discovery began just after the object's evasive maneuvers from the solar wind became evident. Instruments aboard Earth-orbiting observatories started noticing unusual behavior in the heliospheric environment directly behind the object. Normally, a comet's tail disrupts the flow of solar particles for a short distance, creating a wake of turbulence that eventually reassimilates into the solar stream. But behind 3i Atlas, the disruption wasn't resolving. Instead, it was deepening. A long corridor of reduced particle density extended across space like a vacuum channel, and as the object accelerated, this corridor stretched even further, maintaining an eerie symmetry and sharp boundary definition that no natural debris field should possess. Scientists dubbed it a plasma shadow, a term not formally used in astrophysics until now, because it had never been observed like this before. At first, it was assumed this was an optical illusion, caused by scattering or perhaps a fluke in solar activity behind the object, but measurements showed consistent drops in charged particle counts. Detectors aboard NASA's Solar Terrestrial Relations Observatory, STEREO, noted that solar ions were being rerouted, deflected sideways rather than passing through the region behind 3i Atlas. That wasn't passive shadowing. That was field-level manipulation. The structure wasn't merely an absence of particles. It was the presence of something else, something acting like a shield, holding solar wind at bay in a straight, artificially clean void. And what made it more mysterious was that the tail wasn't even active in a traditional sense. No visible gas jets, no consistent ejection trails, no signs of fragmentation that could explain the anomaly. So what was forming this corridor? Some theorized that the anti-tail, previously thought to be a simple geometric phenomenon, was behaving like a charged sheath, repelling ionized matter on a constant frequency. Others suggested that the object might be enveloped in a self-sustaining plasma cocoon, maintaining balance between the forward motion and rear pressure by ejecting tiny packets of magnetic flux. Whatever the mechanism, one thing was now indisputable: particles were afraid of following it. The plasma behind 3i Atlas was behaving like water flowing around an invisible fin. Even when solar activity spiked, the corridor held. It did not fragment. It did not fill. It did not flutter like a normal tail would under solar pressure. It held like a tunnel. Further analysis brought another unsettling detail. Within the corridor, background radiation levels remained stable, but electromagnetic interference surged on fringe frequencies. This meant that the space wasn't just empty, it was doing something. Signals sent across it returned distorted, as if the region behind the comet was not just clean, but curved, bending waveforms, interfering with telemetry. To scientists watching in silence, this was no longer just a comet tail. It was beginning to resemble a trail of influence, a command trail perhaps, or a byproduct of an internal energy field unknown to our current models. The implications were dizzying. If 3i Atlas could sculpt space behind it, clearing out the solar wind, shaping radiation corridors, distorting signals, it meant one thing. It was not just protecting itself from what was ahead, it was clearing a path for something that was following. And whatever that was, it had not yet revealed itself. As 3i Atlas pushed further toward Earth at unprecedented speeds, scientists turned their attention to an invisible structure that stretches out behind our planet like a veil, the Magneto tail. This long trailing extension of Earth's magnetic field is shaped and pulled by the constant stream of solar wind. Under normal conditions, it behaves predictably, fluctuating gently as space weather shifts but never breaking form. That was until the morning of December 16th. At first, the change was subtle, a narrowing in the rear length of Earth's magnetotail. This had occurred during solar storms in the past, but something about the compression seemed wrong. It wasn't caused by high-speed particles slamming into the magnetosphere. Instead, it was happening in the absence of such pressure. And the source seemed to be coming from behind the planet, not from the direction of the Sun. The European Space Agency's Cluster 2 spacecraft, stationed in the far reaches of the magnetotail, began returning telemetry that didn't line up with any previously logged pattern. The tail's alignment had shifted. Normally it wavers slightly, pushed by gusts of solar wind or ripples in interplanetary magnetic fields. But on this day, it snapped into an unnatural shape, a tight, constricted bow that bent as though pulled from behind by an invisible force. Something was tugging on the back of Earth's magnetic signature. That something was aligned precisely with the position of 3I Atlas. What followed was even stranger. For the first time in decades of satellite observation, scientists detected waveform interference not just in the field strength of the magnetotail, but in its oscillation frequency. The tail was pulsing, rhythmically, as if responding to a distant beacon or tuning fork. This was not a solar flare. This was not particle pressure. This was interaction. The direction of the pull lined up almost exactly with the trajectory of 3I Atlas as it approached the orbital plane. Even though the object was still millions of kilometers away, the fields were already reacting. This meant that either the comet was emitting some unknown energy signature that travelled ahead of it, or the void it carved behind itself was somehow coupling with Earth's magnetotail. In either case, the implications were staggering. Imagine Earth's magnetic shield as a long ribbon trailing behind a boat. Normally it dances gently in the current, but now something from across the ocean had snagged the ribbon and was beginning to tug. Atmospheric monitoring stations across the northern hemisphere began reporting minor auroral anomalies, brief flashes of colour in regions where they shouldn't appear. The ionosphere, Earth's protective upper shell, began fluctuating at altitudes inconsistent with any solar triggers. Radio waves reflected strangely, GPS satellites saw minor signal loss, and cosmic ray detectors pinged with rare directional bursts. Everything pointed to the same thing. Earth's magnetotail was being interfered with, not in a destructive way, but in a precise and patterned manner. That distinction terrified physicists more than chaos ever could, because patterns require intention. The antitail of 3I Atlas, once considered a mere curiosity, an optical phenomenon formed by its angle and path, was now acting more like an antenna. The further it accelerated, the more the interference escalated, synchronizing almost like a frequency handshake between the object and Earth. No one was ready to say the word communication, but no one could ignore that the Earth's electromagnetic body was now entangled in a one-way interaction with a celestial visitor we barely understood. What came next would only deepen that entanglement, because as the magnetotail bent and trembled, something else began to shift, not in space, but in Earth's atmosphere itself. Just after the magnetotail began showing signs of abnormal tension, another anomaly emerged, but this time it wasn't happening in space, it was happening in the sky. Over the vast stretch of the Pacific Ocean, where electromagnetic silence is typically maintained, a series of localized high-altitude electrical disturbances suddenly appeared. These weren't lightning storms, nor were they upper atmosphere auroras. What they were defied every known category of atmospheric science. At first, they appeared as faint glowing pulses, soft spherical emissions high above the troposphere, almost at the edge of space. Commercial pilots en route from Tokyo to San Francisco noticed the flickers first, reporting them as ghost lights, dim flashes that didn't move or branch like lightning, but instead swelled and contracted like breathing orbs. Air traffic controllers flagged the events and redirected flight paths, not out of panic, but because of an unexplained radio blackout zone that had begun to widen over the central Pacific. Radio towers on islands like Guam, Kiribati and Midway began experiencing signal distortion that followed a strange rhythm, almost like an encoded frequency modulating in the upper ionosphere. At sea level, nothing changed. The ocean remained calm. But in the stratosphere, strange clouds began to form, not water vapour, not ice, and not volcanic dust. These were electrostatic aggregations, similar to noctilucent clouds, but far denser and more uniform. Satellite thermal imaging showed no heat emission, yet LiDAR scans suggested they had internal structure, coils and filaments like circuits woven into skyborne lattices. And this is when the scientific community could no longer deny the pattern. Every single charge event was directly underneath the vector line of 3I Atlas's acceleration path. It wasn't random. The timing was synchronized. The object had not yet entered Earth orbit. It hadn't even crossed into the geostationary belt. But something about its proximity, and more specifically, something about its anti-tail orientation, was creating electromagnetic responses in Earth's upper atmosphere that weren't chaotic, but geometric. Across international observatories, a consensus began to form. Quiet at first, whispered in private messages between research teams, not yet shared publicly. These events weren't just reactions, they were preconditions. In other words, Earth's upper layers were preparing, not breaking, not collapsing, but reconfiguring, as if they were being formatted, adjusted, tuned. And then came the discharges. Over the course of 10 minutes, instruments on board the International Space Station detected 4 distinct bursts of charged particles rising from the Earth into space, not falling downward from the Sun as they typically do. This reversal was deeply unsettling. It was as though something was pulling the energy up, not extracting it in a destructive way, but sampling it, drawing it in through a narrow vertical corridor that remained invisible to the naked eye. Radio operators in the South Pacific archipelagos began hearing strange static tones in the AM band, tonal, structured, and repeating every 30 seconds, like clockwork. The sounds weren't artifacts of the storms. They matched nothing in known weather patterns or solar interference. They were being emitted, or at the very least facilitated by the atmosphere itself. It no longer made sense to speak of Earth systems as isolated. They were being included, drawn into a process whose logic could not be denied, one that had already started before humans even recognized it. The atmospheric charge events over the Pacific were just the first signs, but they wouldn't remain localized, because just hours after those quiet geometric pulses began appearing over open ocean, they began appearing on land, over mountain ranges, deserts, and densely populated cities. Each event followed the same rules, and those rules pointed to something that Earth had never encountered before, something that didn't need to land to interact, something that used fields, not fire. For weeks, scientists had tried to explain the strange, forward-facing trail extending from 3I Atlas. Unlike typical comet tails that stream behind due to solar wind pressure, this one pointed toward Earth. It refused to behave like any known ion tail. It didn't diffuse, it didn't fragment, it didn't even glow consistently. It pulsed with mathematical regularity. And on the morning of December 16th, a theory began to circulate that would change the way we understood this object. It wasn't a tail, it was a gate. This idea didn't come from fringe thinkers. It came from within a small international consortium of astrophysicists, quietly collaborating since the object's unexpected acceleration event. After running weeks of simulations using particle behavior data, polarization shifts and Doppler distortions, they realized the so-called anti-tail was not ejecting material. It was aligning vectors, specifically directional field lines that responded not to gravitational forces but to inertial opposition. In simple terms, it wasn't a stream. It was a channel, a corridor, a tunnel-like structure that didn't push matter out, but instead bent surrounding space inward, and the direction it bent, always toward Earth. The strange, stabilized field lines forming in the ionosphere over the Pacific began to match the very same geometry found in the anti-tail's core. It wasn't a coincidence. They were mirror images, one in the sky, the other in space, linked by orientation, rotation speed, and alignment with Earth's magnetic north. When they overlaid the data, the patterns formed what looked eerily similar to a bridge, a mathematically symmetrical connection across hundreds of thousands of miles. The consistency suggested a design principle, not accidental, not naturally chaotic, but deliberate. This forced researchers to re-examine the function of tails entirely. If the object wasn't simply moving through space but manipulating the medium of space itself, then it wasn't a comet in the traditional sense. It was an environmental manipulator, a body capable of rerouting energy fields, not unlike how humans reroute electrical currents using copper and semiconductors. But this thing wasn't using wires. It was using space itself as the conductor. The term vector gate began to appear in internal reports, not as a headline, not for the public, but among top-level discussions at JPL, ESA, and a few defense-aligned observatories. It was their shorthand for the observed phenomenon, a fixed, narrow spatial conduit stretching between 3I Atlas and Earth, held open not by gravity, but by inertial resonance and electromagnetic matching. It wasn't stable in the way a wormhole might be described in science fiction. It wasn't glowing or spinning, but it was structurally stable, as evidenced by the repeating fields over Earth, and that made it functional, not theoretical, not metaphysical, functional. And then came the final confirmation, something no one expected. The neutral particle detector on the Parker Solar Probe, which had been repositioned days earlier, recorded a stream of neutrinos travelling against the solar wind. That shouldn't have been possible, but the trajectory lined up perfectly with the anti-tail's orientation. Something was moving through the gate. It wasn't debris, it wasn't radiation, it was structured, pulse-based, and repeating. Whatever it wasn't travelling at random. It was navigating the corridor with purpose. And that raised the final question. Was this a message? A test? Or was something, or someone, already using the gate? The anti-tail was never meant to be looked at from a distance. It was never just a visual marker or leftover dust. It was the key to the entire behaviour of 3I Atlas. And now, it had locked onto Earth. So now we're left with something no telescope was built to explain. An object that doesn't behave like a comet. A structure that doesn't resemble any spacecraft. A pathway that forms without propulsion. And a silence. Unshakable. Total. That only deepens the mystery. On the morning of December 16th, 3I Atlas accelerated by a factor of 33. Not randomly, not chaotically, but in a direct, unbroken alignment with Earth. And at the exact same moment, its forward-facing anti-tail, which we now understand may be anything but a tail, locked into orientation with a newly forming pattern in our sky. And still, no agency has offered a complete explanation. They call it a natural anomaly. They describe the acceleration as an unmodelled outburst, but the patterns are too clean, the resonance is too precise, the symmetry too perfect to ignore. If 3I Atlas is artificial, it's not a message we're hearing. It's a function we're witnessing. It didn't shout. It didn't announce its arrival. It didn't change direction erratically. Instead, it moved with quiet purpose. And what it left behind wasn't debris, it was geometry, a kind of invisible math unfolding quietly, across space, as if it knows exactly where it's going. And why. So what do we do with that? What do we say when something this large, this precise, and this focused drifts silently toward our planet? Not to strike, not to destroy, but to connect. We keep watching. We keep listening. Because sometimes the most intelligent thing an object can do is say nothing at all. This was 3I Atlas. And this was just the beginning.